Cluster architectures seem to be spreading like wildfire as a design framework for the analysis of big data. And one of the main reasons for that seems to be that cluster architectures actually present cloud-level economies of scale, extensibility, agility, and most importantly, performance. All of them very important prerequisites to perform big data analytics. But how does it achieve all that? And how does it compare or differ to traditional enterprise architectures? Well, we believe it is important that you understand the differences rooted in the founding principles between the traditional enterprise architecture and the cluster architecture. The traditional architecture design is based on the assumption that there are three main types of hardware resources to be managed. Servers, enclosing very expensive processing and main memory capacity that should not be idle at any moment in time. Storage arrays, enclosing drives of different performance capacity and cost per gigabyte, ranging from solid-state drives to SATA. And storage area networks, or SAN, connecting a set of servers to a set of storage arrays. One of the beauties of this architecture is the decoupling between the servers and the storage arrays, which can expand, be upgraded, or retire independent of each other, while the SAN enables applications running on any of the servers to have access to data stored on any of the arrays as long as they have the right access credentials. In an enterprise setting, all these architectural components are built to be very robust, and although failure modes are absolutely built in to ensure availability, they are not expected to fail often and are replaced right away when this happens. However, these very properties of a robust and highly available environment drive its value up and demand a premium price. This architecture was primarily designed for computing-intensive applications that typically require a lot of processing cycles, but on just a subset of the application data, which then gets transferred across the SAN from storage to servers for processing, and whose results are then transferred from servers to the storage. Consider, for example, Walmart running statistics and analytics at the end of the day on the daily consumption of milk across the United States. Given Walmart's portfolio breadth, milk is indeed a very small subset of that data. Now, imagine that you actually need to sort big data. And by sorting, we mean to organize the data in a certain order, such as alphabetical order, numerical order, or a time-related order. And by big data, we are referring to 20 petabytes of data per day, as it was the case with Google, well, way back when in 2008. In order to sort data, the entire set may need to be examined, and this is a very data-intensive operation, especially on 20 petabytes of data a day. Now you may ask why you should care about sorting in the first place, and whether or not we could live without sorting at all. Well, consider searching for some information in an unsorted 20 petabyte data set, and you can start imagining the digital version of looking for a needle in a haystack. Sorting is one of the fundamental tasks in computing because once the data is sorted, other operations on the data can be executed orders of magnitude faster, such as searching, merging, and analyzing information. In fact, many believe that as much as 25% of all CPU cycles today are spent simply sorting. Now, if you take into consideration the amount of big data that is being generated through social media and other sources on a daily basis, and that all of this data will probably be sorted first before it gets further analyzed, you should definitely care to understand different architectures being used today for these data-intensive tasks that can support economies of scale, handle big data volume, and deliver the performance requirements of the business. And that's what drives us to the cluster architecture. The cluster architecture was designed with some basic principles in mind. One, to capitalize on commodity hardware, where processing cores and disk drives are at a cost within the economics of the cloud. Now, here's a metric for you. Penny sort. penny sort is a sort benchmark that measures the amount of data that can be sorted for, well, you guess, a penny's worth of system time. According to SortBench, in 2011, the University of Padova in Italy set the penny sort record at 334 gigabytes. And right now, they're saying, give a penny, take a penny, just took 334 gigabytes worth of meaning, or sorting, that is. 2, to enable large-scale applications that are big data intensive, where computations are often done over the entire data set and not just a subset of it. Consider, for example, a genome-wide association study that analyzes the genome of tens of thousands of individuals looking for specific differences or mutations that could be the cause for a particular disease. Now, keep in mind that a genome consists of a sequence of 3.2 billion characters, and now comparing tens of thousands of 3.2 billion character-long sequences, that is big data intensive. And here's another metric for you. Minute sort, a sort benchmark that measures the amount of data that can be sorted in exactly 60 seconds. And according to Sort Benchmark in 2011, the University of California, San Diego broke the minute sort record to 1,353 gigabytes. 3, to address big data requirements which demand high throughput read rate and whose volume can easily render the SAN a bottleneck. And you guessed right, here is yet another metric, gray sort. Gray sort measures the sort rate in terms of terabytes per minute that can be achieved while sorting a very large amount of data. And again, according to Sort Benchmark in 2011, the University of California, San Diego set the gray sort record to almost 1 terabytes per minute at 0.938 terabytes per minute to be precise. And now, that we understand the requirements behind it, let us understand the architecture design. A cluster architecture is based on a set of very simple and basic components that can be available in the thousands or hundreds of thousands and can be easily assembled together. It always starts with a node consisting of a set of commodity processing cores and main memory attached to a set of commodity disks. Then a stack of nodes forms a rack, and a group of racks form a cluster, all connected via high-speed network to enable fast exchange of information. It is important to point out some fundamental principles and benefits of a cluster architecture. First, the architecture is highly modular and scales out beautifully. Keep adding nodes and racks, and the capacity keeps increasing. Second, cluster architectures have the concept of data locality, where data can be processed by the computing cores co-located in the same node or at least in the same rack as the disks where the data is, eliminating or minimizing any data transfer across the network. And the result is that the network is no longer a potential bottleneck. Plus, it naturally drives parallelization of activities, becoming ideal for massive parallel processing type of activities. So going back to the issue of sorting data, each node in a cluster can sort a fragment of the big data that is co-located in the node, and data gets transferred only from the local disk to the main memory. According to the University of California in San Diego, the minute sort record was broken with a cluster consisting of 52 nodes, each node with a 2 quad-core processors, 24 gigabytes memory, and 16 500-gigabyte disks, all interconnected by a Cisco Nexus 5020 switch. Third, the parallelization of disk reads across the nodes may increase the number of IOPS while retaining the same hard disk drive costs. And to understand how this is possible, let us do a simple math here to compare the cost of storage per IOPS between traditional enterprise architecture and a cluster architecture. For these calculations, we will refer to some of the numbers published in March 2011 by Credit Suisse in the article The Need for Speed. And it is important to keep in mind that in this math calculation, the relative proportion between the numbers is far more important than their absolute value, as these values will keep on going down. So let the math begin. In a traditional enterprise architecture, the drives enclosed in the storage array vary in performance, capacity, and cost per gigabyte, ranging from solid-state drive, which, according to the article, are capable of executing 5,000 write IOPS and 30,000 read IOPS, but at a cost per gigabyte in the range of $1.20, to SATA, capable of executing only about 250 IOPS, but at a cost per gigabyte in the range of $0.04. Now, suppose you have a cluster with 120 nodes, each capable of delivering 250 IOPS. Since 120 times 250 is equal to 30,000, the 120 nodes reading data in parallel deliver 30,000 IOPS, the same performance as a solid-state drive, but at the same cost per gigabyte as SATA. Now, all of a sudden, this becomes all the more financially interesting and makes us think about what are the potential caveats. What are we missing? Well, let us see only some of them. The cluster architecture is based on commodity hardware, and the components can and will fail often. So the software managing the architecture and the applications running on them need to detect and respond to failures in an automated and efficient manner. This certainly brings in a great deal of complexity. Second, in order to avoid data loss, typically the data is replicated on many nodes at a time, which increases the amount of storage required to store the data in the cluster. If you have to have 3 replicas of 1 petabyte data, you now need 3 petabytes of storage. And last but not least, in order to achieve maximum leverage in terms of performance and cost benefit, the data needs to be evenly distributed across the cluster nodes. The application needs to be designed within a massive parallel processing style, and careful management needs to be deployed in the exchange of results, intermediate or otherwise, among the nodes in the cluster. Hadoop addresses some of these issues, and that's why you need to listen to the next Big Ideas video on demystifying Hadoop to learn more about how to really harness the value of cluster architectures, and to understand how EMC, being at the intersection of cloud and big data, is strategically positioned to empower you to obtain this value in the most effective manner.